So continuing on of looking at differential equations qualitatively rather than solving for solutions analytically, one major class of differential equations that we could say a lot about are autonomous first-order differential equations. And these equations are important because they have straightforward equilibrium solutions. So many systems are modeled with autonomous first-order differential equations. And their equilibrium solutions are generally seen as horizontal lines, places where the slope is zero, on their direction field. So let's investigate what we mean by all of this further. So what is an autonomous differential equation? An ordinary differential equation in which the independent variable does not appear explicitly is said to be autonomous. Okay? So supposing we could express this differential equation in normal form, an autonomous differential equation has the form dy dx equals fy. Now, what have we written in the past? We've written on the right-hand side that, the general expression would be f of x, y. Here, we're saying no, the right-hand side does not depend explicitly on x. It only depends explicitly on y. Okay, now y does depend on x. It's a solution, right? It's the dependent variable, and so we're going to get solutions y of x. Nevertheless, on the right-hand side there, you won't see an x. Okay, you only see y's. And for this section, we're going to go ahead and assume that f and f prime are continuous on the intervals we look at, just so we could say things from the theorem that we've looked at before, that we're guaranteed an existence and uniqueness of solutions if these conditions hold within a rectangle. So let's look at this differential equation here. On the left-hand side, we've written it in normal form. On the left-hand side, we have a dy dx. On the right-hand side, do we see an x? Do we see the independent variable explicitly written? No. Therefore, it's autonomous. Will we get solutions that depend on x? Yes, but we don't see it on the right-hand side there when we write it in normal form. On the other hand, let's take a look at this differential equation. We look to the right, we see an x. Okay, there's an x right there. And so this is not autonomous. This differential equation is not autonomous. Something to note here, direction fields of autonomous differential equations have constant slopes along horizontal lines. Okay? So we'll see that by looking at the carrying capacity example. Okay, that's a population model. But nevertheless, what is a horizontal line? It's a line where y is a constant, right? The line y equals 2 is just a horizontal line that runs through the y-axis, intersects with the y-axis at y equals 2. Okay? And it makes sense that if you hold y constant, okay, then the right-hand side will be constant, and you're going to get a constant direction field along that horizontal line. So let's look at this theorem here, the translation property of autonomous first-order ordinary differential equations. If y of x is a solution of an autonomous differential equation that you see here, then y1 of x, okay, just another way to label a solution, so we just put a subscript of 1, equal to y of x minus k, where k is a constant, is also a solution. Okay, now what is yx minus k? So this is basically a translation along the horizontal direction of a solution, okay? If k is positive, we're translating to the right. If k is negative, we're translating to the left. Okay? And so that's telling you that once you find a solution to an autonomous first order differential equation, all you have to do is take that solution, translate it to the right, and you get another one. And this goes back to the property that I was talking about of how direction fields of autonomous differential equations have constant slopes along horizontal lines. Okay, so this is tied into it, and we'll look at some examples that'll make this clearer. So before we do that, let's get into another important definition. For autonomous differential equation, we say that a real number c is a critical point or equilibrium point or stationary point if it is a zero of fy, that is f of c equals 0. Okay, these all mean the same thing: stationary point, equilibrium point, critical point. They're sometimes used in different contexts. So f being 0 at the point x equals c. Well, what does f represent? F represents the slope. Okay, what do we know from calculus about points where the derivative is 0? It was called a critical point. So in this context, you look at it as a critical point. Well, these also they'll represent solutions to these autonomous differential equations along horizontal lines, and so they're also equilibrium points. So if you have a solution at a point where the slope does not change, it just stays constant there. Okay, and we'll see this more clearly once we get into example. So find the critical points of dy dx for this differential equation here. Okay, we have fy is equal to 4y minus y cubed. So to find the critical points, we just set that expression equal to 0, factor out a y, and we get these three possible solutions. Y is equal to negative 2, 0, and 2. And these are critical points of fy. Okay? These are critical points of the function fy. Theorem. For autonomous differential equation with f and f prime continuous, if c is a critical point, then yx equals c is a constant solution of the differential equation. Okay? So you got to separate here between looking at this as a point of this function fy versus a function here. Okay? This is now a solution and it's a function. Okay? So these are solutions to this differential equation that are constant. Okay? Here the derivative is 0, and so you do get constant solutions along the critical points. And that goes back to why they're called equilibrium point and stationary point, because the solution is just constant. There's no change going on. The system is in equilibrium. Definition: an equilibrium solution is a constant solution of dy dx equals fy for autonomous differential equation. So this is called a equilibrium solution. Nothing's changing. Our system, which we could represent as a solution y of x, is constant, and so it's in equilibrium. And hopefully now you could understand why I emphasized all three terms for the same concept: the critical point, equilibrium point, stationary point. Okay, because they're just used in different contexts. So if you're just looking at the solutions, you might call it an equilibrium point or equilibrium solution. Critical point if you were just thinking about it purely from the idea of the derivative being equal to 0. Okay, but what is important is that in your mind you separate between finding the points y equals, say, negative 2 that would make fy 0, okay, and hence the slope 0. So separate the idea of that point y equals negative 2, with a horizontal line, y equals negative 2. That horizontal line, y equals negative 2, is a solution curve, whereas this is just a point that would make a function a 0. Okay, so that's why there's also a difference between equilibrium solution, okay, where here I emphasize this is y of x equals a constant, okay? So even as it depends on the independent variable, for any independent variable x we put in, we'll get a constant y, okay? So separate between equilibrium solution and equilibrium point. Remark, equilibrium points and equilibrium solutions are technically different, as the former is a real number while the latter is a function, which is what I'm saying up there. So let's look at an example. Find equilibrium solutions of dp dt equal to p a minus bp, where a and b are positive constants, okay? A and b are considered parameters in this differential equations, which means we treat them as constants, okay? So here we have the right-hand side. We identify the right-hand side with f of the dependent variable here, which is p. Okay, t is the independent variable. And we solve for where this is equal to 0, and it's equal to 0 when p equals 0 or p equals a over b. So we get equilibrium solutions, p equals 0 and p is equal to a over b, okay? These again are just constants. This is a critical point, this is a solution, okay? Note that the equation, okay, that this equation up here, this is called the logistic equation, okay? And we could represent this model called the carrying capacity model of population growth by identifying K, which is called the carrying capacity with A over B, and R with A. Okay, R is the growth rate. Okay, so this is a very common population model for logistic growth that you will run into. So let's talk about phase portraits, direction fields, and classification of equilibrium. A one-dimensional phase portrait is a line that portrays the equilibrium solutions of a 1D autonomous differential equation along with sign of the slopes of the solution curves near the equilibrium solutions. Okay? Again, a picture is worth 1,000 words here, so let's actually start looking at some pictures. So sketch the phase portrait and direction field of the carrying capacity model. Okay, that logistic equation we saw up there. We saw that this has equilibrium solutions p equals 0 and p equals k. Okay. Now if we go and draw the direction field, which we learned how to do, all right, notice what do we put in? The only dependence here is on the y-axis, the p-axis, right? It doesn't depend on the horizontal axis, the x-axis, or here it's going to be the t-axis, okay? So here we have t-axis, p-axis. If we want to know the slope, we don't have to put a t in. Why? Because this is an autonomous differential equation. There is no t. But there is a p. And so we would go along the various values of p that we would put in. So up here, for example, this could be, for example, p equals 1. And we would put p equals 1 in here, and we would get a slope after we fix k and r. You could just, if you want to do a sort of example there, just put in r equals 1, k equals 1, and you'll start getting numbers, which will give you the slope for those particular values of parameters r and k. The important thing to note here, though, is that until we get to k, so this here, This is the point K, P equals K. All right, until we get to that point here, then the slope is going to be positive. How do we see that? Well, here P would be less than K. So anywhere in this chunk here, P would be greater than 0 and less than K, which would mean P over K is less than 1, which would mean 1 minus P over K is positive. Okay? And P is positive and R we assume is positive. And so you'll get positive slopes there. Above K, above P equals K, if we want to plot our direction field, we're going to have negative slopes. Why? Because now P is greater than K, which means P over K is greater than 1, and this will be negative. Okay? Down here for P is negative, which wouldn't make sense if you're looking at a population model because, how would you be getting a negative population? But just for strictly mathematical purposes, when P would be negative, this would be positive, but this here would be negative, and that's why you're getting negative slopes here. Okay? Now, whether the slopes are positive or negative or 0 is what's portrayed in the phase portrait. Okay? So for phase portraits, you'll write down where the equilibrium solutions are. Okay? And where are the equilibrium solutions? They occur at the critical points of FP. When is this 0? When is this 0? This will be 0 when P equals K or P equals 0. And so that's why you're getting these horizontal lines, which are equilibrium solutions. Okay? All right? So this is where the slope is 0. This is where the slope is 0. And our differential equation at that any solution curve that runs through that horizontal line will just be constant. Okay, so these are the solutions to our differential equation. They are constant. So we get these constant solutions that run horizontally. Now, we want to represent somehow to say that the slope is positive in between these two different equilibrium solutions, and that's where the phase portrait comes in. So we'll draw the two different dots here representing the equilibrium solutions, and then we'll draw an arrow that points up here to represent that the slope is positive there. Okay, the direction field flows up. What about above P equals K solution? Then here the slopes are negative, and so we draw a arrow pointing down, and here we draw an arrow pointing down. And what's important with these phase portraits is they're showing you the flow of the solutions. Okay, if we start at some point P here, and we want a solution curve that runs through there, it's going to run like this, okay? Or as you see here in pink, it'll run along like this. Down here, the solution will run down. Down here, the solution will run down. Well, that behavior is being captured by the phase portrait, okay? So first, our solution is up here, it's going down. Well, that's what our phase portrait tells us. It tells us how the solution curves flow, okay? These are flowing down, these are flowing up, these are flowing down. And what you see on the right here is just a breakdown of that. So on the interval negative infinity to 0 for P, okay, so this here, these represent values for P. Okay. Then you have f of P, which is the slope, dp dt, is negative. And so P of t would be decreasing, and the arrow would be pointing down. from 0 to k. So this chunk here, this is from 0 to k. For p, you get a positive sign of fp, which means positive slope, and your arrow in the function's increasing. Solution curves are increasing there. And we could do the same thing for the interval down here, which is negative infinity to 0. We talked about that. Or k to infinity is up here. And we get decreasing. The arrow points down and our slopes are negative. So if we want this to perfectly correspond, we should have actually flipped. We should have wrote this down here and this up here. So some remarks. Solution curves of autonomous differential equations with y prime equals f and f prime continuous must stay within regions bounded by equilibrium solutions. Why? Right? So what we're saying for that first statement here, we're saying, okay, this is a solution curve that's in between these equilibrium solutions. It got to stay in there. Why? Why, when f and f prime are continuous, must that hold? Well, because we have unique solutions. These horizontal lines, say p equals k, is a solution. And so it's the unique solution that runs at any point along this horizontal line, which means no other solution curve could intersect that horizontal line. And so that's what that's telling you. And by the way, up here, the idea of translation, the translation property that we talked about up here, well, that's also just telling you that that would also be a solution. This would also be a solution. This would also be a solution. So these are just translated to the left and right. Okay? I'm not drawing these perfectly, but I hope the point is clear. So that's one statement we could make about solution curves for autonomous differential equations. 2, the solution curves must have exclusively y prime greater than 0 or y prime less than 0. Okay, so you can't, that's telling you that for autonomous differential equations, you can't get something like this. Okay, it can't loop up. It can't have a positive slope and a negative slope. Why? Well, to go from positive to negative, you got to cross 0. And we just made the point in 1 that you're never going to cross equilibrium solutions because solutions are unique. And so you're never going to cross the point where dy dx equals 0. And so you can't hop from negative to positive. Okay? To hop from negative to positive, you got to cross 0. And 0 are equilibrium solutions, and no other solutions cross that because solutions are unique. So that's that. And 3, they'll approach any bounding equilibrium solutions asymptotically. Okay, so as you could see here, they get very close to the equilibrium solutions but never quite get to them. Okay, you have that asymptotic behavior. The equilibrium solutions act like horizontal asymptotes. And again, why is that? Well, if your slope is either positive or negative between these equilibrium solutions, you got to keep going up or you got to keep going down. You say you keep going up, over here you keep going up, right? You keep going up, but you can't ever get to the equilibrium solution. You can't ever intersect it. So what do? You keep going up, but you're only you'll asymptotically approach it. Okay, you'll never get, none of these solution curves in between the equilibrium solutions has a slope of 0. Only the equilibrium solution does. And so you'll inch closer and closer to the equilibrium solution but never get there. Okay, so these are three important consequences of autonomous differential equations. Okay, and this remark here, the axes in a phase portrait represent the dependent variable. That's just to emphasize to you here that this is the dependent variable. Okay. Sometimes this, even though it's the p-axis, will actually be drawn horizontally. We could just have flipped this down and drawn it horizontally. So there's nothing special about drawing it vertically. It is a one-dimensional line. So on that line is the dependent variable, which here is p, and in general we call y. And lines in a phase portrait are called phase lines, okay, and represent the flows of the dependent variables. Our phase lines are just these lines here, and they have over here the direction is down, over here the direction is up. It's more sophisticated, the phase lines. The concept of phase line is more sophisticated when looking at multiple dependent variables. Okay, systems systems of differential equations, you have multiple dependent variables that depend on one independent variable. For example, there it gets a little more interesting. Their phase lines are two-dimensional, and you could see how solutions would flow. But here it's just one line, but we could still represent the how the flows of the solution curves look there. Okay. A critical point of an autonomous differential equation is called stable when any solution curve sufficiently near it asymptotically approach it. Critical points that bring solution curves close to it or towards it are called attractors. Okay, what does that mean? So if we're sufficiently close to this, so let's take a look where this is for critical points or equilibrium points, and we have this equilibrium solution there. Okay, if we start anywhere near here, okay, if we start anywhere near here, where do we go? We approach it. Okay, this equilibrium solution at p equals k has a way of attracting. It has a way of attracting solutions to it. And you could see that by the phase portrait. Okay? Notice how if you have solution curves here, they start to flow up towards k. If you have solution curves here, they start to flow down towards k. That's called an attractor, and it's stable. It's stable because if you're kicked off the, if you look at this from a perspective of the carrying capacity model. Okay, so you look at it as a population model. If you reach your carrying capacity, you just stay there. Okay, the system will just stay at the carrying capacity. What if you get slightly off of it? What if you somehow start with a population greater than the carrying capacity? Then it'll wiggle right back down to the carrying capacity. Not wiggle, but it'll go down to the carrying capacity. Okay? If you start with a population less than the carrying capacity, it'll go up to the carrying capacity. It's stable. A critical point is said to be unstable if any solution curve near it move farther away from it, and semi-stable if some solution curve approach it and others move further away. Points that move curves away from them are called repellers. Okay. So this point here, this equilibrium solution is an attractor. Okay, this critical point is an attractor because solutions go towards it. This is a repeller. You could see that the solutions go away from it. Okay, you start down here. Even if you start so close to that point, to the equilibrium solution p equals 0, you're not going to get to p equals 0. You're going to go up all the way until you get to the carrying capacity. Okay. Likewise, and this wouldn't be true for population models because you can't have negative population, but mathematically, this would go down. The solution curves would go down, and so that critical point is called a repeller, okay? Now, sometimes you'll get situations where, say, if this pointed up, okay, which it doesn't, but if it did point up and this points up, well, you have one of the phase lines going towards the equilibrium solution, another one moving away. It would be called semi-stable. But these two are moving away, and so it's called unstable.